Okay, so in the first part of this lecture, we talked about the importance of electrical characterization of these quantum wells and what we measure, which is mobility and density curves substantially. In the second part, I will tell you a little bit more how we make these heterostructure field effect transistors, and I will give you a couple of examples where we actually measured mobility density curves and correlated them to the structure, to the structural properties of the heterostructure. So here you can see the steps to fabricate an H FET in the shape of a whole bar. So we start from a heterostructure that was grown by RPCVD, as I said before. Then what we do is we put down ohmic contacts. So now the beauty of this germanium platform is that you can put simple metallic ohmics, in this case platinum, and by annealing them in the material, you will form germanosilicides. And because in germanium there is essentially Fermi level pinning of any kind of metals at the germanium valence band, it's very easy to make ohmic contacts. So, and typically it happens at very low temperature, which is very important, for example, 300 degrees Celsius, not to spoil the strain that we embedded in the quantum well. So once we deposit our metallic contacts and anneal them, this can happen either on its own with a rapid thermal anneal, or it can also happen at the stage where you put down the dielectric, in this case aluminum oxide. Once you put down the metal contacts, the oxide, then you put the top gate, maybe type palladium, but also other metals will be okay. And essentially this is the process to make a heterostructure field effect transistor with these quantum wells. So here in the bottom right of the screen, you will see schematics and a cross section in 2 points of the transistor. So below the gate stack, here on the left, you see a nice electron microscope image where you can recognize the sharp quantum well, germanium quantum well embedded in silicon germanium. And then in green, you will see the oxide layer and then the gate stack on top. Now, if we look at the right-hand image, this one here, this is taken as a cross-section through your ohmic contact. You see how the platinum silicon germanium alloy has diffused all the way through the quantum well to provide a nice contact. So in this way, we are able to essentially contact the channel that is accumulated by applying a gate bias to the gate electrode. And now let's look at 2 experiments where we change the structure, so the design of the heterostructure, and let's see what happens to mobility and percolation density. So on the left here, you see an example of a typical germanium quantum well structure. In this experiment, what we did, we changed T, which is the thickness of the silicon germanium barrier that essentially separates the quantum well from the gate stack. So this is a very important metric. And we moved here from 22 nanometers to 55 nanometers. And the curves you see here are mobility density curves and conductivity density curves for these 2 heterostructures. So in red, you see for the what we call a shallow quantum well, so 22 nanometer deep quantum well. You see here that it reaches a mobility of about 500,000, but conduction starts around 10 to the 11. And you see it even better here in this conductivity versus density plot. Once we move the quantum well deeper, what happens is that you still get pretty high mobilities, so above 200,000, but all of this happens at much lower density, and especially the percolation density becomes much smaller. Now, this is very important because by positioning the quantum well at around 50 to 60 nanometers, we get a good trade-off between mitigating the disorder from the oxide interface, so having a deep quantum well, and the ability to impart a strong electric field to shape better our quantum dots. So let's say that 50 to 60 nanometers is found in experiment to be a good trade-off between disorder and stronger confinement. Finally, in this image here to the right, you see both the percolation density in green plotted as a function of the separation T, so which is the thickness of the barrier. This is a systematic study. And you see how it decreases as you are moving the quantum well deeper, down to values of about 210 to the 10 centimeter minus 2, which is a very respectable value. Also plotted here as a function of depth is the or thickness of the barrier is the what we call the saturation density in blue, which is the maximum amount of carriers that you can put in the quantum well, which is an indication of the electric field the quantum well can take. As you see here, what I was mentioning before, the deeper the quantum well, less is the density of the charge carriers that you can put in. So this is a first study to see what happens once you move the quantum well deeper, and essentially you get lower disorder, but if you keep it not too deep, you can also be able to confine charge within the quantum well. Now, the next experiment I want to tell you now is about engineering a better strain relax buffer below the quantum well. So we've seen before the influence of the barrier, now we see the influence of the substrate. So typically in the community, we've been working with two type of heterostructures. This one on the left was the one that brought us to 100,000 mobility, as I mentioned earlier. And how it works is that you start from a silicon substrate, and then you increase slowly the germanium content in the silicon germanium alloy up to the target that you want, let's say 70 or 80% to achieve a nice strain quantum well here. So one disadvantage of this methodology is that it takes a lot of microns material to grow to be able to fill the gradient from 0 to 70 or 80%. Now, another idea is to actually grow directly germanium on top of a silicon substrate. In this way, the gradient is less, it's about 20%, because you have to think about it as a reverse grading. So you go from 100% germanium to 70 or 80%, so the delta is smaller. The disadvantage here is that you accumulate a lot of defects at this bottom interface between silicon and germanium because you need to overcome a 4% lattice mismatch. Now, lately we have been experimenting with these other heterostructures where you actually give up the silicon substrate to start with directly with the germanium substrate, which is readily available also. Now, what we do here is then that we start growth from a germanium substrate, and we do again forward grading, but in this case, the grading is much less. It's about 20%. So you can imagine that this might be an optimal solution to manage the thickness of this strain relax buffer and the amount of dislocations therein. But let's now see what happens to the quantum well from a structural perspective. And here we benchmark back to back two heterostructures that are identical apart from being grown one in the silicon substrate and one on the germanium structure. So here in these other images, you see an AFM image, so an atomic force microscopy image of the two structures. And you can see this these undulations, which are both in topography and actually in strain. And here if you grow on a silicon substrate, you get much more structure and the period is much smaller. And that is because you have much more dislocations that are being managed here to achieve strain relaxation. In the lower image here, if you start from a germanium wafer, the period of this cross-hatch pattern, as we call it, is much larger, which is beneficial. Very importantly, here in these images in the middle, we have etched a bit of material to highlight the dislocations which otherwise would not be visible. These are threading dislocations that come from the bottom to release the strain. Now, in the upper part, we achieve a dislocation density of about mid 10 to the 6, which is drastically reduced if you grow directly on a germanium substrate. And here on the further on the right, you see these schematics which highlight how these random dislocations would be compared to the length scale and to the, let's say, the fingerprint of, for example, a 4x4 quantum dot array. So here in this case, you would have, dislocation, the separation between these locations is starts to become relevant in terms of yield and um, and frequency compared to the size of a device. So you can see that these locations in the long run might limit, let's say, the yield and scaling up of these devices. So it's very important to minimize them. And in the new material, this one grown on germanium wafer instead, the separation is about 13 microns. And so we had a 1 order of magnitude reduction in the number of these locations. So this is really a big improvement from a structural perspective. Now let's see what happens from an electrical standpoint. So once we've done these two materials, we fabricated heterostructure field effect transistors, as I indicated before. And now let's see what happens to mobility and percolation density. So in these three graphs, we show the mobility as a function of density, the conductivity as a function of density, and the mean free path through these three generations of materials. So red and black are the ones I mentioned before. So a shallow quantum well, a deeper quantum well, both on a silicon substrate. Now, what happens if we change the substrate? Well, in terms of mobility, you see a dramatic boost. So you go from a maximum mobility of about 200,000 to more than 3 million. So that's more than an order of magnitude improvement in mobility. Most importantly, you also have an improvement in the percolation density, which now is about 110 to the 10. And overall, also the mean free path that you can calculate is much, much larger in this structure. So overall, you can see that by engineering the structure, either by putting the quantum well deeper or by better engineering the substrate so that it has less dislocation, we got a tremendous improvement in the electrical properties of this material. And this bodes well to better performing quantum dots and hopefully qubits.